Anything you particularly like me to do? Shall I go through the exercise that I thought, well, I labeled as a slightly tricky 248. Yeah, I'd quite like to do that to get that, make sure that's got over. So I propose doing that until you send something else. So what did 248 say? What we've got is kappa is the least weakly inaccessible, which is itself a limit of weakly inaccessibles. Show that it's not weakly Marlow. Actually, in the question, it was called lambda. So it's the least weakly inaccessible, which is itself a limit of weakly inaccessibles. So recall what this meant. It meant you're a regular limit cardinal. So it's kind of the weakest kind of cardinal that we can usually think of that goes beyond ZFC. We can't prove it exists in ZFC. So here's lambda, here's 0, and actually it's not just a regular limit cardinal, but it's a limit of other weakly inaccessibles. So if I look at the weakly inaccessibles below lambda, they're unbounded in lambda. Now you're supposed to show that lambda is still not weakly Marlow. So recall what this meant. This meant if lambda was weakly Marlow, it would mean that the regulars were stationary below lambda. Okay. So to be not weakly Marlow is to say that this set is not stationary. For the set to be not stationary, it means there's a CUB set of points that avoids it. So solution here. So there's a CUB set below lambda, all of which are not regular. Now, a priori, it's not obvious that this here is true. It might be, if I looked at this weakly inaccessible, it's a limit of weakly inaccessibles, there might be some fact of the matter that causes the weakly inaccessibles to be stationary as well as unbounded, right? But the exercise says, no, that's not the case, right? Where lambda is the least weakly inaccessible here. So suppose for a contradiction, lambda were weakly Marlow. Now we've shown in an earlier lemma that this is kind of self-improving. So I think this is lemma 230. Not quite sure if not sure about that number there. 250. That in fact, I can write here that lambda is weakly Marlow if and only if the collection of weakly inaccessibles below lambda is stationary. So that for Marlow, or even indeed weakly Marlow kappa, a collection of alpha less than kappa, so it's a kappa weakly inaccessible, is stationary. Right? Not just the regulars are stationary. So actually, if this guy over here is going to be weakly Marlow, these unboundedly many weakly inaccessibles had better form a stationary set. Right? So suppose let's call it E, the collection of things less than lambda, such that alpha is weakly inaccessible. Suppose this is stationary. Because we're supposing for a contradiction, lambda's weakly Marlow. So using lemma 250, we've got that this here is a stationary set. Then the collection of limit points of E is CUB. Closure of any set is going to be closed. Right? Collection of all limit points of any set forms a closed set. E is unbounded in lambda. So this is CUB in lambda. So, I mean, just one way of writing it is, let's enumerate this. To enumerate this collection, this CUB set here by a normal function. So this is the enumerating function from E star. Now we saw that for enumerating functions for CUB sets, the class of fixed points in the enumeration is also CUB. So the set of alpha less than lambda that are fixed points of the enumeration of any CUB set, or in particular this one, from a CUB in lambda set there. So we call it E bar. So alpha in E bar, f of alpha is alpha. And what does it consist of here? It consists of, well, certainly cardinals, right? Because everything in E is a regular cardinal, it's weakly inaccessible. So this is just a collection of regular cardinals with their limit points. Well, a limit of cardinals is a cardinal. So everything in E star is a cardinal. So we're enumerating these cardinals, the CUB collection of cardinals, by this function FE. Right? So E bar consists of cardinals alpha with order type alpha many weakly inaccessibles below alpha. We're enumerating the fixed points. Right? Alpha is f of alpha. So it's the alphath member of E star here. Right? So they're going to be alpha many, order type alpha many elements of E below alpha. So then what do we have? Right? So what we've got here is these fixed points here. E, right, is contained in E star. Sorry, E bar is contained in E star. Right? This is also a CUB set here. The intersection of a supposedly stationary set with a CUB set is stationary here. But now we have our contradiction. In E alpha, in E intersect E bar. On the other hand, it's in E, so it's weakly inaccessible. On the other hand, it's in E bar, and so in E star. So it's actually the alphath weakly inaccessible. There are alpha members of this set E star below alpha. But that's a contradiction because up here, lambda was supposed to be the very first thing, which was a limit of weakly inaccessibles. Right? So there can't be alphas down here where there are alpha many weakly inaccessibles below it, right? Because lambda is the first place where the weakly inaccessibles are unbounded in lambda. Alpha many weakly inaccessibles below it. This contradicts that lambda is the first such. Right? So the moral of the story then is that this lambda up here is just too small to be the first weakly Marlow. So actually, the first weakly Marlow is much, much bigger than this first weakly inaccessible limit of weakly inaccessibles. And there are other things you can say that are in between such a lambda and this Marlow, but we won't mention that here. Okay. Shall I do some of the other things in the last homework then?
Can I just ask one question about that one?
Yes,
How
sure.
did you show that the E bar was, I think you used to show that E bar intersect E was stationary, you used that E bar was CUB. How do you show that E bar was CUB? Sorry, can you go through that bit again, please?
Sure, sure. It's just I was appealing to a general fact, actually, that we showed that when you enumerate a CUB set, E star, there are CUB many places which are fixed points. So I was using a sort of general, I'll write it out, general fact.
Thank you.
Which I think is an earlier lemma, actually. If you've got C contained in some kappa, kappa regular, C is CUB in kappa here. So you let FC enumerate C. Then if you look at the collection of alphas below kappa, such that f of alpha is alpha, right? This is CUB in kappa. That's kind of what I was using up here. Right?
Thank you. Yeah, that's helpful. I remember that lemma now. Thank you.
Yeah, I mean, it's a lemma and I'm just trying to find its number, but I mean, it's somewhere earlier on in the, it's lemma 213.
Thank you.
Right, so there may be a slightly shorter way of saying this. Maybe this is a bit heavy-handed, but I think that works. Okay. Right, so there was a request to go through 231 part 2 here, which I've written out. Okay, I was just trying to make it a bit brighter because I turn the light on and the camera compensates by closing its aperture, so it doesn't seem to get much brighter. Okay. So actually, okay, in this proof here, so this was part of the discussion about what the H kappa sets are. So just to recall, right? What is H kappa? It's a collection of sets X whose transitive closure has got size less than kappa. So in general, we're thinking of this, of course, for kappa greater than or equal to omega. We're not worried about the finites here. So, and part 1 of the lemma showed that the ordinals in H kappa were precisely kappa, and also that H kappa was transitive. So the first thing it showed was H kappa was transitive. And secondly, it said that any ordinal in H kappa is an ordinal in kappa. So if you want to show that H kappa is, So part one here, the transitivity of H kappa. Here. For A, suppose I've got Y in X in H kappa. I want Y to be in H kappa. But then the transitive closure of Y is contained in the transitive closure of X because it's an element there. This has got size less than kappa, so this has got size less than kappa. Transitivity of Y is less than kappa, so that implies Y is in H kappa. So H kappa is transitive. For B, notice that any ordinal is itself transitive. It's by definition a transitive set well ordered by epsilon. Right? So if alpha is an ordinal, and to be in H kappa is simply to say, right, that its cardinality is less than kappa, because they're automatically transitive. It's its own transitive closure. But to be an ordinal whose cardinality is less than kappa is just to say you're an ordinal less than kappa, because kappa is a cardinal. Okay. And part two, which I wrote out above. Here, we're asked to show that H kappa is a subset of V kappa. Okay, and therefore it's in a member of V kappa plus one. So that's just by definition of V kappa plus one. And the rank of H kappa is precisely kappa. Okay. Okay, so pick something in here. We want it to be in V kappa. Okay, to be in H kappa means that transitive closure of X has got size less than kappa. So we're going to use a couple of facts about X and its transitive closure. Firstly, that they have the same rank. That's an earlier exercise. Well, both of these are an earlier exercise. If X is transitive, then if I look at the rank function applied to X, remember what the rank function does. The rank of Y is an ordinal. It says the least place in the V hierarchy where Y appears. So I apply the rank function to all the elements of X. So that's going to be a whole bunch of ordinals. But if X is transitive, this whole bunch of ordinals is not just a sporadic collection of ordinals. It's all the ordinals up to some point theta or other. So this is a fact about transitive sets, right, that we should be aware of, is that transitive sets contain elements of every rank up to some point, namely the rank of X. So this was proven, well, you can prove both of these by epsilon induction on the sets. So these are earlier exercises. I won't go through these now. It's 1 point something or other. I think I've got written down here. No, I haven't. Maybe it's 111 or something. So we'll use that here. The point is, right, if I've got here a set whose transitive, here we are, sorry, here's a transitive closure of X. So this set has got cardinality less than kappa. And here is rho, it's a function. I could apply this to this set, and it's going to be a function that's going to give me ordinals. It's going to give me all the ordinals up to some point. But the transitive closure of X, its cardinality is less than kappa. So this function can't take a set of size smaller than kappa onto kappa. So theta must be less than kappa for TCX. So I'll just write that down. So as TCX is less than kappa, and the rank function applied to TCX is theta for some ordinal theta, we cannot have that theta is bigger than kappa. Because it will be a function for something smaller than kappa onto kappa. As kappa is a cardinal. So that is going to say that the rank function applied to TCX is some theta less than kappa. So theta here is less than kappa. So the rank of TCX it's the sup of all of the ranks of the TCYs in particular, right? For Y and X. So the sup of the ranks of these plus 1. So this is the rank of TCY is the same as the rank of Y. For Y and X. But all of these things are less than theta. So altogether, this supremum here is less than or equal to theta plus 1, which of course is less than kappa. So I've got that the rank of TCX, which is also the rank of X, is less than kappa. So that puts this arbitrary element of H kappa into V kappa. So thus, H kappa is contained in V kappa. The last part of the thing here is show that the rank of H kappa is exactly kappa. Yeah. So we already saw that kappa was contained in H kappa. So kappa, which is the rank of kappa, is less than or equal to the rank of H kappa. And we want the other inequality here. Sorry, kappa is contained in H kappa, so the rank of H kappa is greater or equal to the rank of kappa, which is kappa, yes. And we've just shown that everything in H kappa has got rank less than. Well, we've shown that H kappa is contained in V kappa. Okay. So one characteristic of rank is that it's the least alpha such that the set is contained in V alpha. Okay. So this here says the rank of H kappa is less than or equal to kappa. So they're equal. And that finishes that part there. Okay. So I suggest looking at 3.1 or 3.2 if I think 3.2 we did in lectures actually. So I'll look at 3.1. This is page 43. Show that X is a total order, sorry, Z is a total of Y can be expressed in a delta zero fashion. Now, I think when you answer this exercise, you can use anything from the lemma above in your reasoning. Can be expressed in a delta zero fashion. So basically, you're being asked to find a delta zero formula that'll encapsulates that idea for us. Right? Okay, so what does it mean to be a total order, right? Right. That I think is all you have to write it down. That's all you have to do is write it down. Right? So what is being a total order is going to be a set of ordered pairs, right? So it's a relation. Right? So being a relation, it's a two-place relation. Something is less than something else. So it's a set of ordered pairs. So the domain of the relation is the things that are less than something, and the range of the relation is a set of things that are bigger than something. So here, we want to say that, okay, so I'm just thinking here out loud. That is a total order, means it's a relation. Right? And what happens is, well, transitivity is going to be one thing. So the field of Z, this is going to be the domain of the relation together with its range. Right? These are things in the first coordinate of an ordered pair in Z. These are the things in the second coordinate of an ordered pair in Z. So Z is a total order of y, right? And we want the field of z to order everything in y. So it better be that this equals y here. So for all uv w in y, right, we should say that, okay, u is in the domain of z or in the range of z, right? So that says, okay, z is going to, okay, so adjudicate something about u, whether it's bigger or less than other things, right? So that's one clause. So as I said, by using things earlier on in the lemma above showed that range and domain can be expressed in delta zero ways. Okay. So what else do we want to happen? Well, I pick any two things, u and v, say. Either v comes before u, or v equals u, or the other way around. Sorry, things are looking a bit like v is looking like u, it's here. So that's saying it's connected, right? Any two things, they're either equal or one is less than the other. And now I just go through the other clauses about what it means to be so that has to happen. And I want transitivity. So, I mean, this in itself is a shorthand for saying VU is in Z. And this is here is saying UV is in Z. And transitivity, I'd say something like, if VU is in Z and UW is in Z, then VW is in Z. So this is just transitivity of Z here. So I want this thing here to happen. Right? And if we want it to be a strict total order, we better have that it's not less than itself. Strict order. So this is saying it's a total order. And this will be true for any u, v, and w. So it's all expressed using bounded quantifiers and using the fact we've already got this as delta zero above here. So using bounded quantifiers makes it delta zero over here. So let's see, okay. I'll do one more from part 2 because I want to do 3, 3. So part 2 just asks you to complete various parts of the lemma that weren't done. Let me just say do 16. This was 3, 7. So 16 said, show x is unbounded in beta. or Z is a function from alpha to beta and is cofinal. So again, using things we've derived for earlier on in the list. So what does it mean for X to be unbounded in beta? It just says for any U in beta, there is a V in X. And these things are ordinals. So, or sets of ordinals right here. Such that U is less than V, which is saying U is a member of V here. So again, just delta zero, bounded quantification here. What is this saying? Z is a function, its domain is alpha, and its range is unbounded in beta. Well, using things that I've already got, this is delta zero. Domain Z is delta zero. So we're just saying that that equals alpha. And range Z, which is delta zero, this is contained in beta. Again, a delta zero relation. But also range Z is unbounded in beta, which we've just done. So we've built this up using delta zero components and didn't even have to quantify. We just used the ideas we already had. Okay, let me look at 3.3, which I think is kind of important. So we saw a lot about, we've talked about how to see that certain concepts are absolute. And we saw that for transitive models, being expressed in a delta zero way means that you're absolute. And we saw that for transitive ZF minus models are a bit more closed, then anything we could express using a definite formula, not just delta zero, but definite formula or term, was absolute. What the exercise here does is just emphasize that the V alpha hierarchy is very special. The V alphas may not be a model of very much, your average V alpha is sort of a V alpha plus one, is not a model of very many axioms. It is transitive, so it's a model of extensionality, but it's not a model of much else. Nevertheless, the V alphas do, of course, contain all the sets. So if there is some, so the idea basically of the exercise here is, here's V alpha, here's a beta inside V alpha. Any function from some gamma smaller than beta onto beta. So any function that shows onto beta here. So this would be showing that the cardinality of beta is less than or equal to gamma. What is this? This is just a set of ordered pairs. First thing from gamma, second thing from beta. If this beta is a limit ordinal, actually F is just a subset of V beta. So as a set of ordered pairs is a subset of V beta. Here. So it's an element of V beta plus one. So as long as alpha is bigger than beta plus one, alpha can see whether beta is a cardinal or not. you just have to inspect inside V beta plus 1. So beta will be a cardinal if there's no such function in V beta plus 1, and V alpha will know it. So if alpha is bigger than V beta plus 1, in fact greater than or equal to V beta plus 1, we've got that beta is a cardinal if and only if it's a cardinal in V alpha. So though I've emphasized that being a cardinal or being countable and so on is not in general absolute, even for ZF minus models, it is for levels of the V hierarchy. And 3.3 here wants to bring that out a bit more. So we take a limit lambda here. So we're only going to consider limit lambdas. Show the following are absolute for V lambda. Right. The power set of X. Right. Alpha is a cardinal, or beta is a cardinal. Okay, so I just did this. Right? What else have we got here? Cofinality of alpha or beta. For alpha is strongly inaccessible. Here, V beta itself or Aleph beta. Or finally, Beth beta. I'm just going to have to turn the light on here. I realize the shadow is not too great there. So again, these are kind of considerations similar to the diagram that I've just drawn, right here. So as I've got here's my V lambda. Here's X. Right. So X is in some V alpha. Alpha is less than lambda. So actually the power set of X is in the next level. Right. So again, alpha plus 1 is less than lambda. So V lambda knows exactly what the power set of X is because it's in here. Right? Therefore, Y is the power set of X if and only if V lambda thinks Y is the power set of X. And that's what we mean by being absolute for V lambda. So a very special case, right? I mean, this lambda may just be like alpha plus omega or something. Right? So this will be this. Yeah. Now we already saw beta being a cardinal. The kind of argument we had there was here was beta. Here perhaps was some smaller gamma. And we had this function f. And there I was saying, well, if beta is not a cardinal, there is a function f from gamma onto beta, right? And that function would exist in v beta plus 1. But exactly similar reasoning does this. Instead of thinking of f as going from gamma onto beta, think of gamma as the cofinality of beta. So f then is a function from gamma cofinally into beta. And f would be in v beta plus 1. So you could say something like this. Note that any function f from beta to beta, where this is a limit, here, f is in v beta plus 1, right here, which is contained in v lambda. So for v lambda to check out what the cofinality of beta is, it just looks at all of the functions like this. So this includes functions from gamma into beta here, gamma less than or equal to beta. They're all here. So v lambda can just check inside v beta plus 1 and look at all the possible functions there are and can check what the cofinality of beta is. So if I've got g from the cofinality of beta to beta, then g is also in v beta plus 1. So v lambda can see what the cofinality is. So if Tor is the cofinality of beta, this is going to be true if and only if Tor is the cofinality of beta here inside v lambda. Sorry, I'm going on slightly over time. I realize this, but hopefully it's to your benefit. I'll just do this one here, because this is slightly different. Aleph beta. What is this saying? It's saying the beta cardinal, right? Suppose y is Aleph beta and y is in v lambda. So we're supposing two things there. Then what is this saying? This is saying that y is the beta in an enumeration of the cardinals. So I see I'm not left enough time for this really. So there is a function f here, which goes from beta plus 1 to the ordinals. So it's 1-to-1 increasing. In fact, it's going to the cardinals. Such that f of Tor is Aleph Tor. So it's enumerating the Alephs. And the last thing here, f of beta is the one we're interested in, Aleph beta. So this is a function from beta plus 1 to this y. So f is going from beta plus 1 here to the ordinals less than or equal to Aleph beta. So again, then f is going to be in v of the next level. And this is contained in V lambda. Because lambda we're assuming is a limit ordinal, right? But Y, this object here, right? It's in V lambda. So it's in one of the earlier levels of V lambda. So V lambda can see from this function that it enumerates all the Alephs up to this gadget. So it sees that this gadget is Aleph beta. Right? So if it's in V lambda can see that it's the beta of Aleph. Is indeed the beta of Aleph. So it will correctly compute what is the beta of Aleph. Sorry, this was a little rushed, I realize, right? Here. The only other comment to make is, of course, if beta is, maybe Aleph beta isn't in V lambda, in which case it's not going to think there is any Y, which is the Aleph beta. So again, it's still true by default. Right?